Sir, good morning, sir. Sir,
Yep.
good morning, sir. Welcome back,
Good
sir.
morning. Good morning.
Sir, we will start in a couple of minutes, sir.
Yeah, fine, fine. I'm ready.
Thank Yes, sir. Thank you, sir.
Girish?
Sir, hello.
Yeah, yeah. How many have joined?
So far, for 43, sir. 43.
Yeah.
Some people are viewing in YouTube, and we will wait for 2 more minutes. 10:05 we will start, sir.
I mean, in the meanwhile, those who
Uh,
are having any doubt,
yeah, yeah.
yesterday's lecture, let
Definitely.
them the question.
Yes,
Let them
sir.
raise the
Yeah, yeah.
question.
Yes, sir. So we request the participants for yesterday's session. If you have any queries, you can post in the chat box, or you can even talk to me for a while. Maybe for 5 minutes. We can have discussion, and then we will move forward for the part two or session, the second session of Professor Muthukumar and sir.
See, if you have any question in the last day's session, please raise the question. I'm glad to answer for your questions. So today we are going to continue the same presentation with case study related to excavation problem. So if you have some question on that, you please raise. Girish, is it YouTube live, this program?
Yes, sir. Yes, sir.
Okay, how is the feedback?
Sir.
Whether you got the feedback about yesterday's lecture?
Yes, sir. Yes, sir. I will be sending today, sir.
Okay, fine, fine. So I think people are not ready to raise the question.
Yes, sir. Maybe they will ask at the end of the session.
No, I'm asking him for the yesterday's lecture.
Yes, 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 sir.
I mean, if you have some sort of issues, any questions in the last day's presentation, you can ask them to raise the question.
Sir, one of the participants posted one question in the chat box, sir. So shall I read the question?
Yeah, I have seen the question. Yeah, whether the same model can be applied to other softwares or only limited to Plaxis. Yeah. I mean, as far as the soil model concerned, these models are available almost in all the softwares when you talk about FEM related softwares. It is not only limited to Plaxis. Any FEM software, you can use all these models. But I mean, each software will have their own advantages and disadvantages. Some of them may not have all the advanced constitutive model, but I believe Moore-Coulomb model is a basic model. Every FEM model will have Moore-Coulomb constitutive model for simulating the soil property. You
Shall we start the session, sir?
I mean, problem specific with the software what you are using.
Sir, we will start the session, sir. Meanwhile, the participants may join in a couple of minutes. We will start the session slowly. Hello?
Shall we start, Harish?
Sir,
Harish?
someone is raised a question. One more question.
Yeah.
Plaxis is better or Abacus?
Yeah. Plaxis is better than Abacus, or Abacus is better, which is it again. It is problem specific. Abacus is a powerful tool where you can have all kind of simulation, not only soil, but Plaxis is especially meant for soil and rock related issues. But still, I can say that each one is having its own merits and demerits. As long as you talk about the soil structure interaction, both are good. Abacus, you have some sort of liberty where you can have your own models. You can develop your own subroutine. You can give your own I mean constitutive model. I guess Plaxis is whatever available. Those things you can use. You can do the analysis. A lot of I mean, with respect to the program specific, FEM program specific, you have many advantages and disadvantages. So finally, you have to select what kind of problem you are going to do the analysis, and your expertise in that particular field, how you are good in doing the simulation. Especially, it's not so easy to do FEM analysis. So though the software is so user friendly, but you need to have a good overall perspective about the software, that you have to pursue proper way of the particular problem and try to implement and try to replicate the problem in your software and try to get the expected result. That is what the important aspect in using Plaxis, using any software, FEM software. So ultimately, you are going to give some input, you are going to get some output. But you should know between the input and output, what is really happening with respect to all these constitutive model, the analysis sequence. So that you have to have a clear idea. That is one aspect. And secondly, whether your output is correct or not, you have to check, you have to do the validation of your result. So basically these things is not so easy. Especially when you talk about soil structural interaction kind of problem, you need to spend more time. You should understand the problem more in depth, and accordingly you have to do the analysis. I mean, my opinion, you have to use, I mean, both are equally good, but only thing is you have to, I mean, some people may frequently use abacus than flaxes. Good, well and good. You have to see what are the constitutive models available, whether you have any opportunity to develop your own constitutive model and do the simulation. All those things you have to check, and accordingly you can go ahead. So both are good. Abacus is much superior from, in overall perspective, where you can have all kind of simulation. Flax is also slowly trying to build up many more add-on to the existing one. It's all completely with respect to the user, how you good in the software. So accordingly, you'll get the good results. I hope I answered your question.
Yes, sir. All right, sir. We'll start the session, sir.
Fine.
Once again, welcome back to all the participants and very good morning, Professor Muthukumaran sir and all other participants. I would like to hand over the session to the Muthukumaran sir to continue his second part of the topic FEM applications in geotechnical engineering with practice. Thank you, sir.
Yeah, thank you so much. Let us continue the presentation what we have started yesterday's class. Uh, but still, maybe if you want, you can decide a little later. So if you want, we can have a break in between. Then we'll continue the presentation. I hope you are able to see the PPT.
Yes, sir.
Okay. So this is what we have seen, where we have stopped yesterday. Have initiated a excavation problem related to different analysis. And in fact, we have seen how the permeability, the soil permeability is going to change overall analysis result. That is what we have seen yesterday. And of course, doing analysis, undrained and drained analysis, in what circumstances we are going for drained analysis, especially the drained undrained analysis will be decided with the permeability. If it is sandy kind of soil, doing both the drained analysis more appropriate than undrained or consolidation analysis. This is what we have seen yesterday. In case you are dealing with the clay soil with a low permeable soil, then considering undrained analysis more appropriate than drained and consolidation. Of course, consolidation analysis will also lead to have results close to the undrained condition. So selecting undrained parameters is more appropriate to do excavation problem in clay soil when you're talking about such a low permeable soil. Okay, let us see a little more in detail. You have a typical problem, so a case study. We are concerned with different soil strata. The top layer is a sandy soil. Obviously, if it is sandy soil, we will be assuming drained analysis, and followed by marine clay. Probably we have to take it, the soil analysis is undrained condition because it's a marine clay. Expected permeability will be very, very less. So it is assumed as a undrained analysis. And followed by the bottom is alluvium, old alluvium deposit. So range of permeability 10 power minus 6 to 10 power minus 8 meter per second. So this layer, suppose you consider drained or undrained, how the results are going to change. Oh, this is what we are going to show. So please don't scribble in the PPT. Okay. If you have any question, you please raise your hand, or you can stop me at any time. You can ask your question. Please don't disturb in
Sir,
the
we can do one thing, sir. There in above, you will have options, sir. Stop annotation. That you can do it, sir. There, if you see in the top corner, more option will be there. Three dots in that stop annotation.
yeah,
That you
yeah.
can do.
Whether who will do?
That presenter can do, sir. You have to do, sir.
Okay, okay. So I am the co-host. I can do. Is it?
Yes, yes, sir. Yes, sir.
Okay. Yes, I did it.
Yeah, thank you. Proceed.
Fine. So now you consider these cases. So different scenario we are taking. I mean, we are doing analysis for considering different aspect. The analysis alone we are going to change. The problem is remain same problem. We are going to do different sort of analysis. The first analysis, scenario one, what we are considering, the sand is drained, clay is undrained, and the aluminum deposit, which is having a permeability 10 power minus 8 meter per second, considering undrained condition. Second, sand is drained, clay is undrained, permeability is more than 10 power minus 6 meter per second, and consider this has been drained condition. So according to the permeability value alone, we are treating whether it is a drained condition or undrained condition. And third scenario, what we are considering, the sand is drained. So obviously sand medium for all three analysis, it has been considered as a drained medium. And clay, it has been taken as an undrained medium. And where we want to see the consolidation effect, so the third analysis, it has been taken as a consolidation medium, consolidation analysis. And for the consolidation analysis, the K taken as a range minus 6 to minus 10 power minus 6 to 10 power minus 8 meter per second. So with this sequence, so we are doing the analysis. What are the implications of conducting an undrained or drained analysis for this particular problem? Assuming marine clay to be drained may not yield a meaningful result, it's a well-known fact. It is complete. The marine clay will have a very low permeability, so it won't drain easily unless you give enough time. So let us move on to this stress condition. So what are the parameters required for doing a total stress analysis or effective stress analysis? So as we are all very well known, total stress is effective stress plus pore water pressure. So we are doing these conditions under total stress analysis involved with the total stress parameters like Cu and phi will be 0 when you are talking about the clay soil under the total stress analysis, and the corresponding undrained modulus and Poisson's ratio close to 0.495. So since we are doing total stress analysis, does not involve pore pressure or increase in pore pressure. So that component will not be there because we are considering in the total stress analysis, pore pressure will not change. So commonly used in undrained analysis in saturated clay soil in the total stress parameters. If you are dealing with the saturated clay soil, when you are doing undrained analysis, so you have to do the analysis under total stress condition. So effective stress approach in clay and sandy soil, as we are all very well known, effective stress is the total stress minus pore water pressure. The pore water pressure is two components. So initial pore water pressure, this initial pore water pressure is with the application of your confining stress sigma C plus delta U. This is the incremental pore water pressure with respect to application of deviated stress. So now, so involve both total stress and pore pressure. So when you do this effective stress analysis, you have a pore pressure component, and this pore pressure dissipation is with respect to time. So involves effective stress parameters like C dash, Y dash, E dash, mu dash, and this is the variability with respect to the soil condition. It is always very difficult to get the accurate value of change in pore water pressure. That is the one is having very big impact on the analysis. For clayey soil, if you are doing total effective stress analysis can be adopted in undrained condition, drained condition and consolidation conditions. So because you are giving enough time to dissipate the pore water pressure. That leads to effective stress analysis. For sandy soil, effective stress analysis should be used only for drained condition. So that is the difference. When you are dealing with clay soil or sandy soil, if you see the previous slide, total stress approach in clay soil, if you consider the total stress approach in clay soil, you have to use the clay's undrained medium. So very clear. In case effective stress, you're considering the effective stress analysis. In case of effective stress analysis, when you are doing in sandy soil, you have to assign the sand as a drained medium. So it should not be taken as undrained medium. It should be a drained medium where you can do the effective stress analysis. In clay soil, it can be a drained medium or undrained medium or consolidation medium because you are giving enough time to dissipate the pore water pressure for in clay soil. Accordingly, you can select with respect to the analysis what you are going to perform. So accordingly, you can select this analysis, effective stress analysis. So undrained clay analysis in clay soil. Suppose you are going to do the undrained analysis. How to do the undrained analysis? What really we need to consider? So it can be a total stress analysis involving total stress parameters in case of undrained analysis. So your total stress is effective stress plus pore water pressure. It can be an effective stress analysis involving effective stress parameters as Moore Coulomb soft clay, modified CAM clay model, or hardened soil model. So what kind of analysis you are going to perform in the clay soil, whether you are going to perform total stress analysis or effective stress analysis, considering your clay is undrained condition. So you have to use the undrained parameters. The undrained parameters handle total stress estimation or under effective stress estimation you have to estimate. Okay. So it can be a consolidation analysis, then you have to work this analysis under time frame. So no volume change, only shear distortion, no dissipation of pore pressure when you considering the undrained analysis. So that is what you have to make a distinguish between undrained and drained analysis with respect to total stress and effective stress parameter. Suppose you are doing a drained analysis in clay soil. So what are the things you have to keep in your mind when you are considering your clay is a drained medium? So obviously, if it is a drained medium, you are end up with effective stress. So effective stress is total stress minus pore water pressure. The pore water pressure is U0 or steady state seepage with respect to time. So it can be an effective stress analysis involving effective stress parameter. So if you do drained analysis, you can do effective stress analysis using effective stress parameter, C and phi value, C dash phi dash. So it can be a consolidation analysis with time as infinity. You have to do the analysis with the time. So excess pore pressure is fully dissipated since we are considering this effective stress analysis, drained analysis. So pore pressure will completely dissipate and the U equal to U0 hydrostatic pressure or steady state seepage pressure is reached. Suppose you are going to do a consolidation analysis in clay soil. So when you are doing drained analysis, undrained analysis, consolidation analysis. In case of drained analysis in sandy soil, you assume if your analysis drained condition, you will be using effective stress parameter and your soil medium will be taken as a drained medium. In clay soil, either you can treat your soil as undrained medium, drained medium, or consolidation medium. So according to this, if you are assuming that your clay soil is undrained medium, you can use a total stress analysis. Drained medium, you have to use effective stress analysis. In the consolidation medium, if you assume that you are going to do this analysis on time frame consolidation, then it is an effective stress analysis involving effective stress parameter. So this is what you have to keep in your mind when you are doing any FEM analysis with respect to this kind of sand and clay soil. So as far as the sandy soil concerned, I mean, you have very less issue or less problem. You are safe. You don't need to worry much. consider the soil is drained medium, use effective stress parameter, do the analysis. It will more than sufficient to get the result, appropriate results for that kind of sand medium. But you are dealing with the clay soil, then you have to little bit careful about the clay response behavior with respect to all these three aspects. Whether you are going to treat as undrained medium where you want to estimate the short-term stability or short-term behavior, or where you are going to have a clay as a drained medium where you are going to estimate a long-term stability or long-term behavior of the clay soil. There the pore water pressure is you are allowing to dissipate, the condition leads to effective stress condition, so you need to use effective stress parameter. And third case, the same clay soil, maybe you can have a consolidation analysis under time domain. So when you use a consolidation analysis, at the beginning of the analysis, your soil will be, take it as under undrained condition analysis. When time is 0, you'll have a build pore water pressure. So that pore water pressure is not instantly dissipated because you are just applied the load. So when the time is 0 or less shorter duration of time, the undrained condition is prevailed. Once the time is increased, after some period, when it's reached to the significant time, all the pore water pressure, build pore water pressure is dissipated, then the undrained become drained. So you need to do this. This is what we have seen yesterday in the beginning. You have seen the graph between time and the pore pressure dissipation set with respect to the settlement. So that is what you need to check. If you are doing consolidation analysis, it is an effective stress analysis involving effective stress parameters. It can generate results for any period of time. That is very, very important. If you do this consolidation analysis, you can able to get the result at any point of time. When time is 0, you are doing an undrained analysis. When time is infinity, you are ending with drained analysis. So this again, this analysis accuracy depends upon the development of pore water pressure or dissipation of pore water pressure. So basically, these are the analysis sequence we need to consider with respect to sand and clay soil, drained, undrained consolidation. And coming to the total stress and effective stress, what really we need to consider. So total stress applicable only to undrained condition. So where you need to use a total stress parameter, where you are treating your soil as undrained condition, that means you are assuming your soil is treated as undrained medium. That means the pore pressure is not allowed to dissipate. So the condition, prevailing condition, the stress development in the soil is stress due to geostatic stress due to soil drain, the self weight of the soil, and the stress due to the water pressure, pore pressure. So you have both the component. So the prevailing stress condition is total stress condition. In the total stress condition, you need to use total stress parameter, undrained shear strength parameter, Cu and Eu. So to create a simple Moore-Coulomb model, you need to have these two parameters, Cu and Eu, to simulate total stress condition under undrained condition. Okay. Suppose you are doing effective stress analysis. So effective stress analysis only to undrained, partially drained, and drained conditions from end of construction to long-term stability. So please remember, you are doing effective stress analysis, but still you can consider effective stress parameter considering your soil as undrained, partially drained, or fully drained conditions from starting from the construction period to end of construction, or even after some period of construction, you can able to simulate the stress conditions in the soil mass. This is purely with respect to the pore pressure generation and the dissipation of pore water pressure. So the parameters required for different cases, the Moore-Coulomb model, C dash, phi dash, and phi E dash, mu dash, and modified clay soil. So you have to use even permeability and advanced volume change. And for effective stress with the strength in total stress, effective stress with strength in total stress, So there, the applicable only to undrained condition where you need to use undrained parameters Cu, Phi and E and mu dash. So this is what basically you have to decide with respect to the specific problem specific, and accordingly you need to use this model. Let us know a little more detail about the Moore-Coulomb model. Whether this Moore-Coulomb model can simulate the real soil behavior. Let us see how the Moore-Coulomb model is going to respond. And what is the real soil response, real soil problem, field problem. So you're all very well known. You're all come across the triaxial test procedure. When you conduct UU test, unconfined, sorry, UU test is unconsolidated undrained test on clay soil. When you do unconsolidated undrained test on clay soil, your strength is independent of confining pressure. So whatever the confining pressure you change, sigma 3 value you change, whether it is 100 kPa, 200 kPa, 300 kPa, your failure stress sigma 1 is always constant. So the response is, the stress strain response is independent of confining stress, sigma C. When you describes this particular elastoplastic behavior, this is a pure elastoplastic behavior. It's a pure representation of elastoplastic response of the soil. This has been treated as the Moore-Coulomb model. So this Moore-Coulomb model you look at here, this has been simplified like this. This is a simplified response of the real soil under UU test. You have a constant modulus, pure elastoplastic. Whereas in case of you are dealing with the drained property, CD test, consolidated drained test, the strength of the soil is purely governed by sigma C. When the sigma C is less, the failure stress also less. That sigma 1 is less. When you increase sigma C value, that is confining pressure, sigma 3 value, sigma 1 will also increase. So that is what represented here. The real soil will have, so when you have more confinement in the soil, confining pressure, the soil can capable of taking more vertical stress. That is what it's shown here. It will take more failure stress. The failure stress is increased with respect to increasing sigma C. So if I replicate this particular real soil response to the Moore-Coulomb model, again, the Moore-Coulomb model is having the same stress time response, and your modulus is constant throughout the failure. Whereas in the real soil field, real soil behavior, the modulus is changing with respect to the confining pressure. Where if you if you convert this real soil behavior to a Moore-Coulomb model response, irrespective of your loading, your modulus is always constant throughout the failure stage. This is what we need to see. So what is really happening when you talk about the elastic model, whether the elastic model going to simulate the real field soil behavior? As we are all very well known, shear stress produces shear strain. This is what a shear stress will do. If you apply the shear stress for any material, the material is subjected to shear strain. The shear strain will try to destroy the material to an angle, but there is no volume change. It has been assumed that the volume is always constant. There is no change in volume, whether it is before strain or after strain, your volume is constant. There is no volume change when you have a shear stress. But unlike shear stress, if you apply normal stress, the normal stress will produce a volumetric strain. There will be a volume change in the soil. This is what really we need to consuming, and we need to apply in this response. What really is going to happen? So can an elastic soil simulate undrained behavior of clay? Let us see. So when you use UU test, you are conducting UU test, undrained behavior. I'm doing undrained behavior. So undrained test I'm doing. When I'm doing undrained test, as I mentioned at the beginning, the diameter of the Morse circle is always constant, but the Morse circle may be shift right and left. This is with respect to the dissipation, with respect to the confining pressure, how much I'm going to apply. So for example, for this much confining pressure, I got this much sigma 1. And for this much increase in confining pressure from sigma 3, 1 to sigma 3 to sigma 3, 3, I'm getting corresponding sigma 1, 1, sigma 1, 2, sigma 1, 3. But if you do that, if you look at the sigma 1 minus sigma 3 difference is always constant. That means your diameter of the Morse circle is always constant. You will be getting same Morse circle. So obviously the failure envelope will be horizontal. There is no change in failure stress. If you look at the corresponding load stress strain behavior with respect to changing deviated stress, change in confining stress, you are getting almost the same response. So this is the simplified version of the Moore-Coulomb model, elastoplastic model. Look at here, this is the real soil behavior. The applied shear stress have a shear deformation or shear strain, and this applied shear stress is not leads to any change in volume. So there is no volumetric strain. So it is a stress independent. So the complete response is stress independent, that is sigma 3 independent behavior. So coming to the simplified Moore-Coulomb model, Moore-Coulomb model, what we are assuming. So shear stress is produced shear strain as like your real soil behavior. And this shear stress is also producing volume change as like a real soil behavior. And if you look at here, the trend is there is no change in volume. So it is stress independent behavior. So if you are dealing with the undrained behavior of clayey soil, your elastic model is more than sufficient to describe your real field response of the soil. So it is exactly to the maximum possible, your Moore-Coulomb model will try to capture the response of the real soil, what you are dealing in the field, because this is completely stress independent response. Okay, what is going to happen when you're talking about actual case? Look at here. So how do we determine the value of E undrained modulus? So in the industry, we'll follow this correlation. EU is equal to 300 times CU. So undrained modulus will be taken as 300 times of CU. If it is a unique value, look at here. If you assume your undrained modulus is an unique value, it is a straight line linear variation. But this is the actual soil response. So this is a real soil response with respect to increasing vertical stress. Now, this is what we need to look into. Suppose this particular behavior, the real soil behavior, is completely stress independent behavior. When the stress intensity is less up to this point, suppose I'm going to compare this particular point where I'm assuming a linearization of your stress response with respect to strain, or strain response with respect to stress. So if I'm dealing with this particular point, my assumption, whatever the E value I'm assuming with respect to the correlation between E and CU, whatever the value I'm using, of course, I'm using a constant value. That value is exactly simulating or predicting the actual response of the soil when the stress level is this much. If the stress intensity is more than that, then my Moore-Coulomb model is predicting, overestimating the soil response than the actual soil response. If the stress is less, then my real soil behavior is, the actual one is higher than the estimated one by Moore-Coulomb model, or Moore-Coulomb model is underestimating the actual response of the soil. So this is what we need to see. If you have linearized your model, to some extent, your Moore-Coulomb model is working very well. So well within the expected response of your soil, it is basically underestimating. So you don't have any problem where the soil will behave much better than the predicted value. So your values are underestimated. So you are in the conservative side. But if your stress is beyond this point, your real soil behavior is going like this. It is completely nonlinear response. Whereas your FEM model using Moore-Coulomb model is going to predict, estimating, it is overestimating the actual response. Finally, the real field is here, but this is your FEM analysis. It has been overestimated, so you will be in trouble. So when it is underestimated, you are in safe zone. You are in conservative side, no need to worry. But if your FEM model is overestimating then the real behavior, then we are in trouble, because by using this result, your soil, by the time your soil might have reached the failure stage, you will be end up within a problem. So this is what basically we need to look at the real response of the soil with respect to the change in modulus in soil. Let us go a little more detail. What exactly we are doing using Moore-Coulomb model with the hyperbolic model. Look at here. Generally, this is a range of selection of your E value. So under undrained condition, so 100 to 500 Cu. For any value of Cu, you have selected a constant modulus. So this is a constant modulus variation. When you use a hyperbolic model, the hyperbolic model is basically, this is a real soil response, whatever you have seen here. It's a complete nonlinear soil response. So with respect to the change in modulus, you have to pick up, if you look at this in the real scenario, so wherever you have change in curve shape, so that modulus, a tangent modulus will be taken for each change in level. So that will give the complete response of your soil with respect to load intensity. For example, I'm going to apply the load intensity of this much, only this much. So taking this modulus is more appropriate. From here to here, if I use apply load, taking it is a changeover, use another modulus. So hyperbolic model will give the change in modulus with respect to the stress level. This is very, very important. So when really you want to use hyperbolic model, when really you want to use Moore-Coulomb model. So there are a lot of difference between these two. So when you assume the Moore-Coulomb model, you yourself assume that the soil is having a constant E value. When you are selecting hyperbolic model, you are setting that the response of the soil is stress dependent behavior. It is not stress independent behavior. So accordingly, with respect to the stress level, your modulus will also change. Okay, so let us see with a typical example how this we can demonstrate with respect to an excavation problem. Look at here. I have an excavation, so I'm going excavation with staged construction, staged excavation, stage 1 to 4. I'm going with a staged incremental excavation. If you look at here, when I do the first stage of excavation, how much stress I'm releasing in the bottom of the soil and how much pressure, active and passive pressure is mobilized in the wall. So accordingly, the wall deflection will be measured. Look at here, the soil modulus changes at various stages of excavation. You really pick up the soil wall deflection with respect to, assume that you have a complete instrumented wall, where each stage of excavation you are measuring the wall deflection, and with respect to the depth of the wall you are plotting the wall deflection. So this is the wall deflection. Let us assume the first stage of excavation, this much is the wall deflection, and stage when it is increased second, third, fourth, those are the corresponding wall deflection. Now, using this wall deflection, you can back estimate your sustained response of the soil, and clearly you will end up with a hyperbolic mode. So if you back calculate E value, E value will give in this way with respect to the stage of construction. So according to the state of stresses in the soil, the modulus is also going to change. It is not a constant modulus. Now let us see. But we'll go a typical problem with respect to the comparison between Moore Coulomb and hyperbolic model, what we are going to deal. So assume that you have a soft clay with the CU value of 30 kPa, where I want to go 8-meter excavation. So excavation is done in staged manner. So assume that each stage of excavation is 2 meters. So I'm going excavation with the stage by stage. Let us just compare that what you have already predicted in the linearization. What I have used, EU is equal to 120 times CU. So using this constant approach, my response has been developed. So this is the linearization of my E value with respect to any excavation stage considering Moore Coulomb model. So this is the Moore Coulomb failure envelope. So this is the Moore Coulomb model response with respect to stress and strain. And this is the actual nonlinear behavior that already I have obtained this response in the real condition, the real field condition. Okay, so this is the nonlinear response. Now, for this stage, I'm going to use, I'm just doing one stage of construction, just I'm doing excavation of 2 meters. So first 2 meters has been excavated, then the wall deflection has been measured. So this wall deflection I am doing from the FEM. I'm trying to capture the wall deflection using these two modulus. So first I'm using the modulus. I'm doing an analysis with the Moore Coulomb model using this representation of stress strain. Okay, this elastoplastic behavior, Moore Coulomb model. So in that case, the wall deflection is larger. So if I use this portion, this linear modulus is less than the initial modulus of nonlinear curve. So this is actual soil response. So where in the actual soil response, the initial modulus is much higher than the modulus what I have selected for Moore Coulomb model. So obviously, Moore Coulomb model will yield more deflection than the actual soil hyperbolic model. So the nonlinear deflection, I mean, when I use nonlinear model, deflection is less than when I'm doing just a 2 meter excavation. So now you have to see, if I do the 2 meter excavation, what is the state of stress in my soil? That stress level is really very less. Maybe it is less than this level of stress. Where that level of stress, the real soil modulus is much higher than the linearized model, Moore Coulomb model E value. So obviously your displacement is more when you are using Moore Coulomb model than the hyperbolic model. Let us move further. Now I'm doing for the second stage of excavation. I have gone up to 4 meter depth. So when I do the excavation up to 4 meter depth, I have measured, I have obtained the wall deflection corresponding to the 4 meter depth of excavation. The corresponding hyperbolic nonlinearity has been used and the corresponding E value has been taken as this level. This is the corresponding tangent modulus for the second stage. Look at here, this E value is corresponding to this tangent point, which is more or less very close to the Moore Coulomb tangent point. So we are getting almost same wall deflection. So whether you use Moore Coulomb model or hyperbolic model, Whether you are dealing with the linear problem or non-linear problem, your wall deflection is same, is expected one, since you are dealing with only your stress level is almost in this level where both the modulus are more or less constant. Suppose I am going for 8-meter excavation where I am doing the deep excavation. So when I go for the deep excavation, so my stress level in soil is very high. So the corresponding hyperbolic model E value is very, very low. So this is the corresponding tangent modulus. So if I use this tangent modulus for this particular state of stress level, my deflection is very, very high than the Mohr Coulomb deflection. So this, again, the Mohr Coulomb, I'm still using the same modulus. So that deflection is only this much after having 8-meter of excavation. Whereas in this nonlinear model, hyperbolic model, using this E value, this is the real one when you are going, when your stress is increased. So the deflection is almost 26% higher than the linear model deflection. This is what really we need to see in the excavation problem. So basically we are moving the stiffness of the soil from this level to this level. So here it is a very steep where you have a high stiffness. When your stress is increased, your stress strain relation is more flatter and flatter, and the tangent modulus is drastically reduced compared to the initial modulus. You are moving from this zone to this zone, this level to this level, with only the change in stress in the
There might be some technical issue. Just hold on, dear participants. Sir will join now in few seconds. I request the participants to kindly hold on. Maybe some technical issue with the expert. He will shortly join. Yes, sir.
Am I
Sir,
audible
continue, sir.
now?
Yes, you are audible, sir. Our screen is not visible, sir.
Yeah. PPT is not visible, is it?
Yes, sir.
Is it visible or not?
Now we are able to see you, sir. PPT we are not able to see. Share the screen.
Okay.
Yeah.
Maybe I'll reconnect. Are you
Now it
able
is visible, sir. Yes, sir.
to see now?
Yes, sir. Please continue.
Yeah, fine. Fine. So when you do, I mean, larger excavation up to 8-meter, so that is what I was trying to tell you. So the modulus is changing from this initial stage where you have a very high modulus to very flatter modulus. So between these two range, you have the real soil response. So that somehow we need to missed out in case of Mohr Coulomb model. So this is what I wanted to emphasize. When your stress level is low, then using Mohr Coulomb model is in the conservative side, you don't have any issue. When the stress level is more, when you are in the zone, using the Moore-Coulomb model with the linear elastic behavior may not be able to pick up the real soil response, where we may completely end up with a mismatch and we may be in trouble and our system may get disturbed. Okay, so different softwares, how the value of E has been taken with respect to CU value. Okay, so let us move a little more detail what exactly is happening with respect to these two, linear and nonlinear response. At the final stage of excavation, the relevant modulus may vary from project to project. That is what level of excavation you are going to deal and what will be the corresponding change in modulus. That will change to project. That means with respect to the soil specific what you are going to talk. And basically this is a correlation you can use and calculate the value of soil modulus. Okay, let us move on to the applicability of Moore-Coulomb model for drained condition. So the undrained condition we have seen in the beginning. So where undrained condition, the modulus is independent of stress. So Moore-Coulomb model can be very well used to predict the soil response. But suppose you are doing undrained analysis. When the undrained analysis, you know that the shear strain will produce a shear stress will produce a shear strain, and the shear stress will produce a volumetric strain because the pore pressure is allowed to dissipate. So once the pore pressure dissipation is taken place, there will be a change in volume in the soil structure, and the peak stress is always function of sigma C, the confining pressure. So you can look at here, the modulus is not constant. It's keep on changing with respect to stress level. So the real soil field is E value is stress dependent, it's not stress independent. If it is undrained analysis, the E is stress independent value. Drained analysis, your E is stress dependent value. Suppose you resemble this into pure elastoplastic model, typical Moore-Coulomb model. So if it is the Moore-Coulomb model, shear stress will produce a shear strain. Shear stress, there is no change in volumetric strain because you are assuming a constant modulus. And normal stress will produce a change in volume. So you can see here, the E is stress independent. So whatever the value of stress, your E remains constant. There is no change in E value. So it is a completely stress independent value. So this is what basically we need to look into it. When you simulate the drained condition, in case of drained condition, the modulus is not independent. It's not a independent value, it is a dependent value, stress dependent value. Whereas if you use a Moore-Coulomb model, your E will be always treated as an independent value of stress. So that is a big conflict within the linear model like a Moore-Coulomb model, non-linear model like a hyperbolic model. So which model really we need to use with respect to this model? So what are the implications when you are using this model? It may not produce the correct information if you use drained analysis using Moore-Coulomb model. You may not have a proper result, and result may be sensitive with respect to the Poisson's ratio, and we are very well known determining the Poisson's ratio is very difficult, and it may not produce the correct pore pressure response. When using C-5 as a consolidation analysis, it may generate the wrong undrained shear strength, though we are doing drained strength. Okay, so let us see what exactly it is happening when you're talking about the simulation with respect to the field problem. Suppose I'm considering a soil element here. Let us say this is my soil element. Let us say the soil element is A. I'm going staged construction, staged excavation, stage wise. I'm going a 4 stage of excavation. Each stage is 2 meters. So I'm going for a total 8 meter of excavation stage. So assuming assume that when I'm doing the first stage excavation, the corresponding stress strain relation is this for that particular soil element of A. This is a stress strain relation. And if I take the modulus corresponding to this stress strain relation, approximately, and stress soil condition when I'm going for the excavation. Suppose I'm going stage by stage excavation, assume that I have reached to the fourth stage, where my last stage excavation has gone very close to the soil element A. And if I draw the stress strain variation, from this stress strain variation, I'm getting E as only 3. This is what really we need to look into that actual problem. When the excavation is very low, very small depth, my soil is having more modulus. When the excavation is going deeper, my modulus is reduced to almost 3. So from 20 to 3, how much the modulus is going to change with respect to the depth of excavation, that is what we wanted to simulate. If I use the same 20 modulus here, my wall deflection will be remains almost very less compared to the actual wall deflection, because I have used very high modulus, where I completely missed out the real soil behavior. That is the problem. So you look at here with respect to the different stage of excavation, how the modulus is changing with respect to stress. Let us see what exactly is happening. Now with this simple stress path method, we can able to ascertain using which stress path zone Moore Coulomb model is really picking up the actual response, and which zone is highly dangerous one and which zone is not possible. Look at here. I'm talking about this soil element somewhere how same. Considering this particular aspect, the excavation problem, assume that the soil is having this much strength. This is the failure envelope. This is the strength available in the soil. Without doing any excavation, any disturbance, the soil is subjected to K0 at rest condition. Doing some sort of excavation and construction, loading, unloading, the stress path will change with respect to the K0. It can change any of this direction with respect to the change of state of stress level in the soil mass. What it means, when your zone is fall, stress zone is fall in F category, that is a really danger zone to pick up the real response when you use Moore Coulomb model. And of course, E is a questionable zone. Let us see what exactly is happening. So suppose you have a soil element where you are considering soil element. One is in the excavation side, the other one is rear to the excavation side. So both soil A and B, with respect to the locality, the state of stresses will be uniform before doing any excavation. Okay. So whatever the sigma 1 the same amount of sigma C, so it will be in equilibrium state. And similarly, A will also be in the same way. Sigma 1 and sigma 3 will be same before doing the excavation. Once you start to do the excavation, basically you are reducing the overburden pressure of the soil. And with respect to this excavation, the rear side of the soil is subject to active earth pressure. So assume that this is the failure envelope of this particular soil, the whole soil mass. And according to the at rest condition, this soil A and B is lying here and here. So this is at rest condition of your soil element A and B with respect to the state of stresses. For example, if you talk about A, the overburden pressure is less, sigma 1 is less, So you'll have a corresponding sigma 3, and this is the point what you are getting in the failure envelope. And B is deeper in depth. Obviously, it will have more sigma 1 value, so it is higher, it is increased. When you start doing the excavation, sigma 1 value is drastically going to reduce because you are removing the soil overburden. So B will drastically moving to this area. Your sigma 1 is going to reduce, sigma 3 is also going to reduce. So it will going to shift towards the left side and touches the failure envelope. And this is the movement of your stress path with respect to the soil element B. And with respect to soil element A, this is the movement of stress path. Now this is what basically we need to. So both is leading to the failure stage with respect to the staged construction. But which soil element is moving which direction and which is the critical one according to the excavation problem. That is what. So basically, if you look at this is what it is happening. Can your elastic model simulate a real soil behavior? So undrained condition with the total stress analysis, the elastic model can produce a reasonable result. So using undrained condition with the total stress analysis, the elastic model can produce a reasonable results. That is what we have seen. Under drained condition with the effective stress analysis, the elastic model can produce reasonable result for certain stress path zone A to D. Zone A to D, A, B, C, D. In this stress zone, stress path area, you don't have any issue. Your model is very well predicting. This is what I want to mention. With respect to this Moore-Coulomb model, this is the actual stress strain response. So if your stress path is within this region, you can able to some extent, whatever the response you are predicting is acceptable according to Moore-Coulomb model, what you have used. This will give more clarity with respect to that statement. Zone A to D. The result involving stress path in zone E may be questionable, and result involving stress path zone F is unreliable. This is what, so basically you have to see when your stress path is in this zone. So this is the really unreliable zone. What you can see from this, actually this zone is unreliable zone. So when you are like, when your stress path is lying in this zone, so we are really dangerous. As per Moore-Coulomb model analysis, it will lead with the failure. So can we trust the result of Moore-Coulomb in soft clay? This is what linear elastic model will give. Assume that if you are using linear elastic model, these are the corresponding reflection using linear elastic model. When you use a hyperbolic model, this is the actual deflection. So there is a huge difference between these two when you're seeing the real clay. This is what finally, when you are using Moore-Coulomb model constant E value, your real soil behavior is in this way. So you must understand the shortcomings of the soil model used with respect to the problem specific. So accordingly, you need to select a particular constitutive model for the analysis. So coming to some of the problems related with practical problems related with CD analysis, and what kind of circumstances we need to go for a consolidated drained analysis. Suppose you are constructing an embankment. The embankment construction is a slow process one. So like you are constructing embankment. So just you see the animation time what I have given, it is very slow process. So probably this 2 meter or 3 meter embankment I have constructed for 6 months time. So by the time, whatever the soft soil I have, whatever the pressure I imposed, overburden pressure, the pore water pressure will be developed. That pore water pressure is allowed to dissipate during the 6 months of construction time. So then I'm going for the second stage of construction. So the construction is basically a slow process construction. So whatever the pore pressure which has developed in the soil, the developed pore water pressure is allowed to dissipate. Then the prevailing condition leads to drained condition. So the strength which is available, what you're talking in situ drained shear strength, where you are going for slow process construction. Suppose an earthen dam with a steady state seepage. So assume that this is the earthen embankment. So if the reservoir is full of water, the seepage is a steady state of seepage. So unfortunately, it is not working. So the water level drop down is very steady state. What I mean to say is, suppose the water is going out, it is seeping, water level is drawing down. Assume that the first 1 meter is dropped by 1 week time. So that means whatever the pore pressure created in the outer core of the embankment or dam, by the way of 1 week time is will be dissipated and no more pore pressure in the outer core. So it leads to drained condition. So assume that the next 1 week water drop down to another 1 meter. So whatever the pore pressure which is inside the soil mass is allowed to dissipate. So your dropping down is having some time to dissipate the pore water pressure in the earthen dam. Then the earthen dam stability will be under undrained, so drained condition stability analysis. Okay. And third case where we are doing the excavation and natural slope construction with slope process. Again, if the excavation is done with the slow process, you are ending with drained analysis and construction of slope strained analysis. So CD tests simulate the long-term conditions in the field. The CD and 5D drained parameters should be used to evolve the long-term soil behavior. So where do you want to do CU analysis and CU parameters? Suppose the embankment construction rapidly over a soft clay soil, but construction is rapid. So during the process of construction, your pore water pressure is still there. You are not allowing the pore water pressure to dissipate. So the condition leads to undrained shear strength. So again, drop down is very quick drop down. You are not giving enough time to dissipate the pore water pressure which is inside the earthen dam. So the condition prevailed is undrained shear strength condition. And any construction, fast construction in the slope leads to undrained shear. So the total stress parameter CU test, CCU or C5U, can be used for stability problems where soil have become fully consolidated and are at equilibrium with existing stress state. Then some of the reasons additions to stresses are applied quickly with no drainage occurring. So the condition prevailing is undrained condition. So wherever you do rapid loading, rapid construction, the dissipation of pore water pressure will be a slow one. I mean, you are not giving enough time. So again, UU test. So even we are not giving enough time to dissipate the pore water pressure during the time of initial construction, that the consolidation process. So UU test is completely unconsolidated, undrained. It's a complete rapid construction. Finally, you need to have undrained parameters. So the prevailing condition is undrained condition. So UU test to simulate the short-term condition in the field. The CU can be used to analyze the short-term behavior of the soil. So with that, we have come to the end. So let us move on to the question session.
Yes, sir. Thank you, sir.
Yeah, please.
Thank you for your nice presentation. Now I'll open chat box to the public participants. I will request the participants to post your questions in the chat box, or you can even unmute yourself and talk.
Yes, please. You can post your questions or you can unmute your mic and ask questions. Yes, a presentation will be shared. So the coordinator will distribute the presentation to you.
Sure, sir.
Of course, you can distribute the recorded video also to
Yeah, yeah,
everyone.
sure, sir. Sure, sure. I'll do that,
Yeah,
sir.
yeah.
The session is open to discussion. The participants are requested to post your questions.
How stress increases with increasing depth of excavation? Um, I don't know what sense this question is asked. Let me briefly explain. This stress is pertaining to the wall movement. So when you do the excavation, obviously the supporting wall will have more deflection. This deflection is coming because of the wall is subjected to more active pressure. When you go deeper and deeper excavation, so obviously the lateral pressure on the wall is more and more because you have more active earth pressure. So that will increase the stress in the soil mass. So the deeper the excavation, you have here the problem is related to excavation. It is basically unloading. Excavation basically is unloading, but loading with respect to the wall. Okay, wall is subjected to load. So because of that load, the wall is subjected to deformation. You have more deformation in the wall. So that is why increasing the excavation will have more stress on the wall. So obviously when the stress is more, deflection will be more. Uh, you see one question.
Sir, what are the precautions should be taken? Rapid excavation or rapid, sir?
Yeah, fine. So this is very, very important aspect we have to keep in our mind, whether it is excavation as well as formation, loading or unloading. Both rapid conditions will have a severe impact on the soil stresses. Especially when you talk about saturated clay soil mass, you have to check the stability over a period of time. There are two approaches. You know your in situ stability of the soil. Suppose you are going to do a construction of 2-meter embankment. Actually, you want to build a 10-meter embankment height. The 10-meter embankment height, you are not going to have a single stretch. You will be doing in stage by stage. So you have to make a correlation between the strength gaining from the soil with respect to dissipation of pore water pressure for the applied overburden pressure. So based on that calculation, you have to decide what will be the rate of construction. So for example, first 1 month, assume that I am going for 1 meter fill. For that 1 meter fill, what will be the strength, shear strength gaining due to the pressure dissipation? So that you need to have a correlation between these two. So second month, you instead of 1 meter, you can go 1.5 meter. By the time your soil gaining, if it is 10%, it's more than sufficient to take another 2-meter height. So you have to work with this calculation. One aspect where you are not very keen with time escalation or your project time itself, you have some years, maybe 2-3 years, your construction project. So according to the construction period, you can divide how much fill is required. For excavation problem, of course, if it is a large excavation, you need to have a proper cut-off wall like a diaphragm wall or sheet pile wall with cross strut. And with that, the stability needs to be checked instantly. What will be the developed wall movement or bending stress which is coming from the excavation site, and what are the locations is severe. That is what normally we will do in the deep excavation. You have to have a proper protection structure such a way that you can accelerate the rate of deepening or excavation. So you have to have one-to-one correlation comparison. I hope I answered your question.
Good morning, sir.
Yeah, someone asked general guidelines for validating results of analysis. Advice on I
Yes.
don't know. General guidelines. Yeah, of course. So basically, when you're using FEM, there are so many procedure you need to follow. Doing an FEM is not so easy. So you have to follow certain procedure. First you have to identify proper constitutive model for that particular problem. And before doing the actual field problem, you try to take any problem which is available in the literature, most probably any field study. You try to conduct a field study. Field study data you can input in the FEM, do the analysis, get the result, and try to compare this, validate your model, develop a model. You have to do convergence study in terms of mesh convergency, selection of soil model convergence study with respect to available result. The result is benchmark for you. The benchmark results will be compared with all this kind of parametric analysis. And finally, you have to adopt, which is the one with close to the field results that should be used for your parametric analysis. So you have to do a validation.
Good
Any
morning, sir.
questions? Yeah, please.
Sir, first of all, I would like to thank sir for your nice presentations. But only I have one question, but it may be wrong, but you correct me if I'm wrong. So
Please.
whatever what is that the study we have done so far, you explained this. So in practical case, we have already decided the depth of excavation as well as the founding, what is that safeguarding capacity of the soil in case of any foundation designs. Then what way the study, whatever you have discussed so far, in what way it will benefit or it will give any what is that effect on that? I'm correct.
No. Your question is correct. Your question is excellent. Okay. Two aspects. You have decided something unknowingly. Clear.
Yes.
Your foundation is you have done the soil exploration. You have done the soil test.
Even by assuming that is the what type of soil it is there, in normal design, if you take any practical foundation design, so based on the soil, we are not for a shallow foundation only. It's not high-rise building or the ordinary residential building. We are never what is that think over on the soil exploration test or nothing. Based on this, what is that? Experience will decide the depth as well as the based on which we have designed this the foundation. It's actually
Okay.
I may be wrong, but I want to convey something, but I'm not in correct way. But you please.
No, fine. Are you a practitioner?
Not sir, but just
No. Just I wanted to know. Are you a practitioner or
I'm an academician. Sir. You're an academician.
Okay,
I'm
fine.
working as a lecturer in some government polytechnic college.
Okay, fine. No problem. But your perspective is completely wrong. Even if somebody does, it should be avoided. Okay. I used to say that the guesswork, whatever you have mentioned, it's absolutely correct. That is what many practitioners are doing. That should not be. So there are two aspects pertaining to your question. One is ignorance. People are very lethargical with respect to soil test or spending little money towards getting a more optimized system. People are not ready to spend little time and money. I say that whatever you are looking in the outside, your building or whatever it may be, the construction, you are just looking the external appearance of the construction after the construction. But the beauty is not only the external appearance, it is a performance. It is also equally important. The performance is equally important. Appearance may be good, short duration of time. If at all your foundation is resting on a weak problematic soil, over a period of time you will have a cracks. So cracks will widen, develop. Over a period of time your complete appearance will collapse. So now your beauty is gone. So this is what I normally used to emphasize. Whatever it may be, it is a lightly loaded structure, small structure, one-story building or many-story building, doesn't matter. You spend some money and some time for doing a proper investigation, explore the soil, and sometime by doing a small investigation, you may be able to get a more appropriate foundation system, or sometimes it may be more optimized foundation system where you can able to save your money. There are two things. In general, soil, it's something like your human body. If you calculate the stress at this level, I mean the neck level, the neck is subjected to only the head stress. Whatever the head weight, only that much stress you will have in that neck. If you go down with your body, at any place down, your stress will be more because the weight is more. That is what exactly happening in the soil. If you take 1 meter depth, the soil is subjected to 1 into gamma stress level, 2 meter, 2 into gamma, 3 meter, 3 into gamma. Fortunately, your strength is increased with respect to depth, no doubt. If your bearing capacity is 50 kp at 0.5 meter, it may be 75 or 100 kp at 1 meter. This is what the reality, because the effect of overburden. So that's why many people have simply do the guesswork and I mean without blind work. They will put some numbers and they will do SPC calculation again. But 90% you won't have any issue, because this is the reality. Using more depth, you are obviously you are getting more resistance, no problem. Your SPC is high, you are getting it clear. But the unfortunate thing is, sometimes you may be problem where your unit weight is not going to increase with respect to depth, because when you are dealing with heterogeneous soil mass, where you have a water table effect, where you have a soft clay packets, and these things is completely the governing one, your bearing capacity. If you use that thumb rule, you will be end up with some sort of issue. Finally, your system will collapse. This is what finally you have to keep. So maybe to emphasize further, I will say that doing such a way of approximation of your SPC or depth of foundation is something like a guesswork. So 5 clients are touching the elephant. You know the story. When the blind is touching the elephant on their parts, they will feel on their own. Sometimes it may be looking like a snake, crocodile, wall, but the complete picture is elephant. So unless you spend time and money to see the complete picture of the elephant, you will always end up with a small other animals. So that should not be, guesswork should not be done, especially when you talk about heavy infra. So obviously heavy infra, nobody will do the guesswork, but still many issues are there. But now doing a soil investigation is mandatory. You have to do it for getting the approval, especially for getting the house loan and other things. Bank loan, you have to submit a investigation report also.
Two
Nothing
after
spending
the
little
two
time
after.
and money to do the complete analysis. Fine, you can continue your question.
No, no, sir. Thank you, sir. Thank you very much, sir. That too after Maulivakam accident is that's it must be the mandatory for getting the structural.
Yes, yes, we have to do it.
Yes.
See, engineers, we should enforce, we should insist them to send the client to do it. So client, after all, they will see what way we can save the money, but engineer, we should not compromise. We should ask them to, I mean, we have to explain what is the pro and cons with respect to these things. So we should get best out of that.
Thank you very much, sir. I admired with your presentations, even though I'm an academician, but I really admired, sir. Thank you very much, sir.
Thank you so much.
Any other questions from participants are requested, and please.
Girish, can you look at the chat box? There are
Yes,
any
sir.
questions?
No questions so far, sir. I am looking at it, chat box, sir.
Okay.
So we request the participants, if at all any queries that you have left, you are welcome to unmute yourself and talk, or you can even post.
So any more question, you please post your question, or you can ask the question.
The feedback and all I will send again, but ask your question so that we can have the discussion part.
Sorry, can you give, if you want to give a project work for our students, which type of areas you can give, sir?
Sorry, I could not able to capture your question. Please louder.
Sir, can you, in our area, in our students, suppose I want to give in a project work, so for BTech level, which type you can give, sir? For BTech level projects, sir?
Okay, first you have to see what are the facilities you have in your institute. Okay, and look at the students' potential also. If some people are really good, you can give a good problem to get out of some good research also. So don't think that BTech students
okay,
can
sir,
also
actually,
do a lot.
okay, sir. One more requirement, sir.
Yeah.
In our college, we have MTech Geotechnical Engineering, sir.
Good.
So in MTech Geotechnical Engineering, suppose I want to give a project work in earthen dams. So
Yeah.
it is actually in earthen dams, it is related to water resource, but in combination with geotech as well as in the water resource, which area I want to use, sir?
Absolutely,
For
you can
MTech.
you can do a project on that. There are so many areas still not explored much. You can try. Do some proper literature survey, and accordingly you can fix the problem.
For CPACE failures, I want to give CPACE failures or like can
That's
give, sir?
fine, but the thing is, I mean, it's very difficult to do some sort of field study.
Sir.
Only thing is, you try to get some field data nearby area where you have a earthen dam.
Sir.
Using that, you can do some sort of FEM analysis. Using Flaxis, you can very well do CPH
Actually,
analysis.
in our area, actually it is in Rayalaseema, sir. In our
Yeah.
area, one Atham dam is there, sir, in our nearer to our district. So actually, in last years, we are preparing a model for Atham dam, a small model in our laboratory, and then we are calculated some sequence losses like that. But you may not get, the results accurately, sir. So how if you go into the field, how you can collect the data, sir?
No, it's very difficult. I mean, with the BTech students, you can't get because it's a
For
time
MTech,
dependent MTech project.
MTech,
Yeah. You can engage some of the people to. I mean, it's not so difficult to get the data. You have to have some sort of field instrumentation
sir,
where you can get the approval from the authority. You can do some
sir,
field instrumentation in the dam to monitor the. You can install piezometers to monitor the pressure and
sir,
pressure variation. You can theoretically you can simulate the periodic line and you can see how much seepage flow is happening. And if possible, you try to do a flow net diagram. From the flow net diagram, you can theoretically estimate the seepage loss and overall quantity measured with the overall capacity of the dam. With respect to that, you can able to simulate FEM analysis and correlate whether you are able to get the actual quantity estimation. But it is a tedious process, but still you can use, if any real field problem, if you take and solve, it's really helpful to the society. You can
Okay,
try.
sir. Thank you very much, sir. Thank you.
Sure. I think there is one question. Only
Yeah,
SPT be enough to prepare soil test report if correlations stand properly? So for your information, as of now, most of our investigation is only with SPT. Almost 90% of our foundations are sitting on SPT results. So there are two reasons. One is the method is well established, well reached to even bottommost level. The cost involvement is very less compared to other tests. And the most important aspect is you can able to see the sample visually. You can collect the sample and do the test in the laboratory. You can make a correlation 1-to-1 field and laboratory results, and you can come out of good correlation from the SPT. But SPT is one of the most rude method, very rough method. So it involves several uncertainty, starting from the verticality of the drill rod and the height 76 centimeter, weight 63.5 kg. So you have to ensure all this measurement in order to have a proper result. And the energy dissipation, energy loss, corrections with the diameter of the borehole, correction with the air drill rod, correction with the liners of the spoon. So many things are involved in SPT. Even in spite of all this uncertainty, still we are using SPT because it is somewhat reliable then and somewhat economical than using other method. But nowadays there are so many sophisticated non-destructive equipments are available, but the only drawback is it will mislead you. You have to have a combination of destructive and non-destructive. You can have a collective comparative study with destructive and non-destructive test, and as much as possible, big projects they used to have a combination of all the things: SPT, CPT, and van shear test, where you have a soft soil pressure meter test, and some sort of non-destructive also for big project. But small projects, obviously, keeping all those equipments will be costlier. It may not be affordable for a small project. So with SPT is more than sufficient. But the only thing is you have to do the SPT properly. As much as possible, use auto trip SPT where your errors will be minimized. And using that SPT and value, do the proper corrections. And of course, you'll be getting the samples, disturbed samples. Using the disturbed samples, estimate all the rest of the parameter in the laboratory. Make a correlation between the SPT results and laboratory results. Bring out a good geotechnical investigation report. It's more than sufficient for any small level project.
Yes, sir. All right. So I think we will stop this for here, sir.
Yeah.
So I request if anybody is having query, we'll give 1 more minute. So
Yeah, if you have any
anything-
questions, you can ask, please.
Yeah, well, sir, we will stop it here. Maybe they can even send me mail, then I can
Yeah,
even
please.
forward
If
to
you have
you.
any doubt, you can send the mail either directly to me or the coordinator. We are ready to clarify your doubts at any time. Thank you so much.
Yes, sir. Thank you so much, sir. I am actually I went back to our NIT Trichy days. I was there for 6 years, and I am very happy and fortunate to have you as my professor and sometimes guide as well. I could recollect all days, sir.